Up here, we're going to learn another important line involving circles, and that line is a tangent line. A tangent to a circle is a line in a plane of the circle that intersects the circle in exactly one point. So it is a line that touches the edge of the circle at one point, and only one point. But if it touches more than one point, then it's a different type of line. The point where a circle and tangent intersect is called the point of tangency. An important theorem to know about this is that if a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So when you have a tangent line, so in this diagram here, AB is your tangent line. Here's our tangent. It's hitting a circle at exactly one point, point P. That is our point of tangency. Okay? If we draw in this radius OP, okay, the tangent is perpendicular to the radius, which means what kind of angles are formed? 90-degree angles. So the tangent and the radius always makes a 90-degree angle every time. Okay? Important theorem to know. And we can use this theorem to help us solve problems. It says in the circle, what is the value of x? Okay? Well, what kind of lines are LM and NM? What kind of lines are they? You're right. They're tangent because they're only touching the circle once. And we know what kind of angles are formed at L and N if they're tangent to the circle. 90-degree angles because it's intersecting at the radius. So because they're intersecting the radius, we know those are 90-degree angles. Okay. If we know both of these are 90, what do we know about a four-sided figure? What do all the angles of a four-sided figure add up to? 360. So we can do 90 plus 117 plus 90 plus x, and that's going to equal 360. And then you just solve for x. Right? Just like we would have done with a triangle, but instead of saying 180, we would say 360 because it's a quadrilateral. Okay. Combine your like terms, what do we get when we do 90 plus 90 plus 117? 97. Plus x equals 360. Move the 297 over, and what does x end up equaling? There is a shortcut to this problem. Does anyone notice the shortcut maybe based off our answer and the angle across? They add up to 180. So that's a shortcut. Okay? Whenever you have kind of this quadrilateral made by two radii and two tangents, okay? Whenever you have that, there's actually a shortcut rather than doing all this work. Okay? You can do all that work, that's fine. We don't remember the shortcut. But the angle here and the angle across from it, so this central angle and the angle across from it are always going to be supplementary. Those two angles are always going to add to 180. Okay? Because these are both 90. 90 plus 90 is 180. So subtract 180, you get this plus this is equal 20. So just a shortcut. The angles across from each other. When you have this quadrilateral formed by two radii and two tangents, these are always supplementary. So you could have just done 180 minus 117 and still gotten 63 degrees. Either way is getting you the trick. One's just a lot less work than the other. Okay? Questions? We want to find the value of r in the circle in our next example. Okay, well, I just have two r's and I need to find them. What do you know about the shape that was formed? Triangle. Specifically, what type of triangle is it? A triangle, because we have that 90-degree angle there. Again, 15, this line that's representing 15, it's a tangent. It's hitting the circle one time. And it's also intersecting the radius. So we know that angle right there is a right angle. Well, how do we find missing sides of right angles? Pythagorean theorem. So I know this is the missing side that has r, so I know I can use the Pythagorean theorem to find it. Remember, which side has to be RC? Hypotenuse. Then it doesn't matter, I'll make that my A and that my B. And you just plug it in the Pythagorean theorem, which is A squared plus B squared equals C squared. We said our A was R, so I'm going to write it as R squared. We said our B was 15, I'll write it as 15 squared. Here's the thing with our C. What's our C? Perfect, 9 plus R. Okay? Because from here to here is 9. This blue part is 9. The green part is the radius. That's what we're trying to find. That's what we don't know. So you have to write it as 9 plus R squared. That whole thing squared. So be super careful when simplifying this down. We can't really do anything with R squared, so I'm just going to leave it as R squared. Plus, what's 15 squared? How do we have to write that? Be super careful. Perfect. Because we're squaring this, you have to write it twice. It's really tempting to just distribute that exponent and say that's 81 plus r squared. That's not right. That's not correct. It's tempting to do that, but it's not correct. Okay? Whenever you're squaring a binomial, okay, you have to write it twice, and then what? Foil, or double distribute. Okay. So I'm going to keep this side exactly the same. I'm going to keep it as r squared plus 225. Foil. So when we do that, 9 times 9 is 1. 9 times r is just 9r. Should do that. R times 9 is 9r. And then r times r is r squared. If that bothers you, that it's like backwards. You just rewrite it as r plus 9. That's fine. It's not going to change your answer. Okay. Then go through, combine your like terms. Again, I'm going to keep this side exactly how it is. Can't really do anything with the 81. 9r plus 9r is what? Squared. And we're just solving for r at this point. What's going to happen to those r squared? They cancel out. You have the same thing on both sides. It always just drops. Because if I took this r squared and moved it over, it cancels. Well, it's also going to cancel there. They just cancel out. So now, that makes our lives a little easier because we're not dealing with those r squared. We just have 225 plus 81 plus 18r. Alright, are you going to get r by itself? Move the 81 over. What's 225 minus 81? 143? 444. Divide by 18. So our radius is that's an important one to know how to do. Questions over there. Again, the biggest thing with this one is just remember to FOIL here. And then those r squares are always going to drop out for the most part. Questions? Okay. If you flip it over to the back, it's the same theory we've been talking about, but in reverse. So on the front we said if a tangent is, if a line is tangent to a circle at the radius, it's perpendicular and it creates the right angle. So this is just flip-flopping it. So this is saying if a line in the plane of a circle is perpendicular to a radius at its endpoint, then that line has to be a tangent. So just going back. Okay, so if you have a line that's perpendicular to a radius, then it has to be tangent. Okay. We can test this out. Okay. We're trying to decide if ML is tangent to circle N at point L. And in order for it to be a tangent, what angle does this have to be right here?
Right.
Yeah, it has to be a right angle in order for that to be a tangent, but we can't tell if it's a right angle, we weren't told it's a right angle. But what kind of shape do we have in that diagram? A triangle. And if we can show that it's a right triangle, then we know that's a right angle, then we know it's a tangent. How do we think back? How do we show that something's a right triangle? Not use SOHCAHTOA. Yeah, we're still going to use Pythagorean theorem, because the only reason why we can't use SOHCAHTOA is we never use it from the right angle. If we were trying to figure out the measure of m or the measure of n, you are 100% correct. You'd use SOHCAHTOA. But because we're trying to find the measure of L, we can never use that for the right angle. It just will never work. So we're still going to use the Pythagorean theorem. Okay? And we're still going to plug all those numbers in. And if it works out, if we get the same number on both sides, it's a right triangle because those numbers worked in the Pythagorean theorem. If you don't get the same number on both sides, then we know it's not a tangent because it's not a right triangle, which means that's not a right angle. So which one has to be our C? 25. The biggest one, the one we're assuming is our hypotenuse, is 25. And then it doesn't matter which one's your A and which one's your B. No, just make that A, that B. Could have flip-flopped it and you're fine. So you can do this in 2 steps. You can do it all in one. You can just do 7 squared plus 24 squared in your calculator. What do we get when we do 7 squared plus 24 squared in our calculator? 625. Equal to what's 25 squared? We got the same thing on both sides. Is this a right triangle? Yep. So is this a tangent? Yes. Because it's perpendicular, it's creating the right angle. So yes. ML is tangent. Circle. If you got like 600 equals 625, then no, it's not a tangent. Because it didn't work in the Pythagorean theorem, which means it's not a right triangle, which means it's not a right angle. It can't be tangent. Questions over that? Couple more, I think. $108. 122. Oh. Got what? 14 minutes? Put it in there. I'm just trying to think of things. Let's do this last one first. Well, okay, we'll just do it. Two tangents, so another theorem. If two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. So we take a look at this diagram. Segment AB and segment CB are both tangent to that circle. And they're both coming from the same point. Looks like an ice cream cone. That's how I like to think of it. If you have this ice cream cone type of shape, automatically we know that those two segments are the same. Okay? So if you have two tangents and they're coming from the same point, so it's kind of like making an ice cream cone, we know that those two tangents are equal. Okay? If you have two tangents to a circle but they're not coming from the same point, then they're not going to automatically be equal. Okay? And we can prove this. Go ahead and take your 2 pounds. As always, my favorite thing. Okay. And we were just given this diagram. That's what we were given. just to save us some time. We're given the diagram. Okay, but we're pretending like we don't know that they're equal. Okay? That's what we're pretending. We're acting like we don't know they're equal, that's what we're trying to prove. Okay? And I'm going to draw in a couple things. We don't have to state that we're drawing them in our proof. I'm just going to draw them in because they're there. Okay. Well, what do we know about these two statements right here? AO and OC. They're equal because they're both what? So that's why I'm drawing it. I'm going to go ahead and draw in those radius because they're technically there in the diagram. We're just drawing them in so we can visually see it. Okay? So what we're going to do first. Okay? We know AO is congruent to OC because they're both radii of that circle. So that's what you're going to write as your statement. Radii of the same circle are congruent. Okay. Radii. What do you mean?
Like, because we did AO and OC. Should we not go outside?
It says OA, OC. Okay. You could have said AO and CO. That's fine. Are congruent. We know that. They're going to be the same. Okay? So that's so far what we know. And what we're going to do, I'm going to mark that. Okay? And it is really nice with trying to prove these type of theorems. A lot of the times we prove that what are congruent. You might notice that what two shapes are congruent. Triangles. We do that a lot. Is there something we can draw in to give us two triangles? A line, right? We can connect O to what? B. Let's draw that in. Now do we have two triangles? Yes. So we're going to draw OB. And what's our reason when we ever draw a line in? 2 points. So now we have two triangles, and we just proved that one part of that triangle are congruent. Okay? We need to prove some other parts. Is there any other thing we can say is congruent? It's congruent to OB. OB is congruent to OB by what property? Yeah. OB is congruent to OB by the reflexive property. Now I'm going to highlight this out. We technically don't know that these are congruent. We don't know. I'm going to color them out. Nobody can see. They're there, but we don't know. That's what we're trying to prove. Right? So act like those 6 marks aren't there. That's what we're trying to prove. But we know that by the reflexive property, the shared side is always congruent to itself. Is there anything else like angles? Anything? Yeah, why do we know that they're right angles? Good, yeah. So we can state that. We can state that angle BAO and angle BCO are right angles. Okay? And our reason for that is just we know the tangent is perpendicular to the radius. Okay, we know that. Tangents.
You just saying definition of a tangent?
That's not technically by the definition of tangent, it's just it meets the circle at one point. That's it. There's the theorem states that it's perpendicular. So you have to kind of shorthand and state what that theorem is. Tangent perpendicular to radius. Something along those lines. Well, what did we say whenever we say two angles are right angles? What's always our next reason every single time?
Angles congruent.
all right angles are congruent. So we're going to state that next. We're going to say angle B. Okay, actually this one's sorry. We don't have to state it. I have it. We don't have to state it. Because if these are right angles, we know these are right angles. What kind of triangle makes those two triangles? What type are they? Yeah, they're right triangles. Okay? So we know those are right triangles. Can we stop right now and say that these triangles are congruent? Yeah. Because some of you are thinking, well, can't we state that those angles are congruent and then say side-side angle as a reason? Can't use that. That might be the direction you're going, but we can't say side-side angle. Okay? And side angle side doesn't work. So what we can do, because we show that those are right angles, okay, then we know that triangle AOB and triangle OCB are right triangles. We said they're right angles. Triangle CCO are right triangles. By definition of a right triangle. Okay. So then, think back to that unit 3. Whenever we have a right triangle, what shortcut can we use to say that those triangles are congruent? It's 2 letters. Look at your diagram. What is it? HL, yeah. We showed the hypotenuse were congruent, and we showed that leg was congruent. So hypotenuse leg, HL, lets us know that 2 right triangles are congruent. So we can state that. Now we can say that triangle BAO is congruent to triangle BCO by hypotenuse leg. And now that we know that the triangles are congruent, we can state that their parts are congruent, which is what we're trying to prove. We can say that AB is congruent to CB. Those 2 tangents. By what's our reason? Questions over there. One more. Quick one. So because of this, we can use it for circumscribed polygons. A circle is circumscribed about a polygon if the circle contains all the vertices of the polygon. So if the shape's inside the circle and the vertices of that shape are touching the edges, it's called circumscribed. Okay, so you did those constructions when you drew the circle around the triangle. That was a circumscribed triangle. A polygon is inscribed if the circle in a circle, if each of its vertices lie on the circle. So if the circle is inside the triangle, then it is inscribed. Okay, so when you drew the circle inscribed, when you did your construction, you constructed this. Drew the circle inside the triangle. Okay? So when this happens, when you have any figure, we predominantly work with triangles, and the circle's inside that triangle, okay, all these parts just became tangents, and we're trying to find, in this example, we're trying to find a perimeter. Okay? So this right here is tangent to that circle. This section right here, these 2 lines are tangent to that circle, and these 2 lines are tangent to that circle. And these 2 green lines both come from point A. These 2 red lines come from point B, and these 2 purple lines come from point C. So what do we know about the 2 distances of the green lines? They're what? They're equal. So if that one's 10, what's this one going to be? 10. If this one's 15, what's that going to be? And if that's 8, what's this going to be? 8. That's true. Doesn't matter if triangle or any other figure. We'll mostly work with triangles. So I have a circle inside this triangle. These two pieces, so the parts that are next to each other, are going to be the same because of that tangent theorem. So when we find the perimeter, you can add up all those little pieces, or I just double them. So like 10 plus 10 is what? 20. 15 plus 15 is 30. And then 8 plus 8 is 6. I just double the pairs. So you just double it and then add it. 20 plus 30 plus 16 is what? 66. So the perimeter is 66 centimeters. Questions over that? Okay. I'm sorry. Ooh, 1 minute to spare.
Yeah, last week.